Okay, this is our lecture number 13 and in this lecture we're going to take a look at a couple of problems, how single population hypothesis test is being conducted. Alright, again we're going to start with examples that deal with numerical data, and in the next lecture number 14 we're going to look at hypothesis testing when the data is categorical, and we're really testing statements about the population proportion. Again, simply because for categorical data, calculations of the mean do not make sense. Even if we assign numerical labels to different categories, computing the mean will be meaningless. Sort of. Mean is meaningless, right? It's kind of funny sounding. Okay, anyhow. Example from accounting. A department store manager tries to determine that if a new billing system, computer-based billing system, computerized, will be cost effective, and he believes that it will only pay for itself, will be only making sense to install the new computerized billing system if the average monthly account is more than $170. So in other words, if they have enough business so that manual accounting labor becomes too expensive, then it makes sense to install some enterprise resource planning system and do accounting using the computer programs instead of manually. So that's the idea. So that person, the department store manager, selects randomly 400 accounts, and what's being recorded down is the balance. The amount of money that are accumulated every month on the account. So the data are stored in the file accounts.csv. Alright. So question is, can we conclude that the new computerized system will be cost effective from this data, right? From the data recorded, can we conclude that new computerized accounting information systems will be cost effective and therefore it's worth the investment? Okay, that is our research statement, right? Should we install the new computerized billing system? And that boils down to the question about the average monthly account, right? If the average monthly account is higher than $170, then we will install the system. Otherwise, we will not. Right? And in the previous lecture we discussed that the way how we formulate hypotheses is we always start with alternative statement. Why? Because the alternative statement is the expression, is the mathematical expression of the research question that we are trying to solve in the problem. So in this case we're trying to solve, is that true that the average account balance is more than $170? So if that's true, then we go with the accounting information system, right? That becomes our alternative statement. There it is. That the average balance is more than 170. In this case, the executive decision is to install the new information system. Otherwise, if it's 170 or less, then we just keep using old, manual system. Okay. Before we begin, well, actually, let's go ahead and do that right off the bat. Okay, so RStudio, right? We're going to use our tool, and I'm going to create a new R script from the clean page, right? Empty page. Okay, first things first, of course, we have to always read data from CSV file. Okay, so I'm going to call it accounts data. Okay, and read.csv, just like we always do. Gonna be fancy today. File equals. Okay, and in quotations, I have to specify fully the location of the file, right? So disk C, folder data, and the file is called accounts dot comma separated values. When I run this line, there it is. So let's take a look at the structure str of the accounts data. Not required to do that, but it's just good practice. Okay, so right here at the bottom it says that I have one column, one variable and it's called accounts. So these are just different balances, right? For 400 different accounts. Well, nothing unusual. Problem pretty much states that. Okay. So before we go into the hypothesis testing, what I want to do is emphasize that we are trying. Let me switch back to PowerPoint. Right. We are trying to test the population mean. Right. So our hypotheses, both null and alternative, are about the population mean mu. Very simple statement. It makes sense to test hypotheses about the mean only in cases when mean is useful. What does that mean? Well, if my data are distributed in a weird way, like for example, the data distribution is extremely skewed to the right or to the left, or it has several peaks, so it's bimodal or trimodal distribution, or something like that. And in this case, I can formally calculate the population mean. But is that useful, really? So if, for example, my data is bimodal, so there is one peak and there is another peak, the mean probably is going to be in the valley between the two peaks, right? And the mean should be the representation of the center of the data. Well, how can my mean be the representation of the most typical number in my population if I have valley in the histogram? If anything, mean is going to be a bad way to represent the population, right? Because I have very few numbers like that. So therefore, all these tests of the hypothesis for the population mean, they can be carried out, and they make sense only when my data is well behaved. If you remember from a couple of lectures ago when we discussed the confidence interval, I told you that one requirement for the confidence interval to be useful is that data must be normally or approximately normally distributed. So if data is non-normal, bimodal, trimodal, very skewed, then mean kind of loses its attractiveness. It's not a good way to talk about the data anymore. So same thing applies, actually, same consideration applies for the hypothesis testing. So before we proceed, before we start doing the hypothesis test, we need to take a look at the distribution of the sample. If the sample looks normal, then my data, where it came from, the population data, probably is also normal, because sample is like a small representation of my bigger whole, which is population. Okay, so I'm going to leave a lot of comments as I normally do, right? Construct histogram to evaluate normality. And for now, that's what we're going to do. Okay. Actually, in the same very lecture, right now, well, not right now, but sometime. In some time, we're going to discuss yet another different way how we can check for normality. But for now, we're going to just plot the histogram and see if it's normal or not. So, as always, I use HIST, right? So my data is called accounting data, accounts data, and the column is called accounts. So I plot the histogram, and there it is. So what do I see? Well, it's not perfectly normal, but then again, I never expect something to be perfectly normal, right? Normal is just a idealized kind of thinking about the world. Something is normally distributed is never true, right? It's just idealistic, too good. But is it severely abnormal? I wouldn't say so. It's a unimodal histogram. There is only one peak. It's fairly symmetric. Oh, it's not perfectly symmetric, but fairly symmetric, and it goes bell-shaped, right? So therefore, it's not too badly non-normal. Okay, good. So I can go ahead and proceed. Okay, and in this slide, basically, that's exactly what I'm discussing. Next slide. Okay, and this is the picture that we just saw. Distribution is fairly normal, so I can go ahead and proceed. First of all, remember what we discussed in the previous lecture, that my sample is evidence about my population, right? So here's what I'm testing. I'm testing the challenging alternative hypothesis, right? That my mean for the population, okay? I'm testing the mean of the population is higher than $170. That's what I want to see, okay? And the evidence if that might be or might not be true, whatever that is, should come from sample. Well, let me go ahead and calculate the sample mean, right? So, and I'm going to call it, how about I'm going to call it average. I don't want to use the word mean because mean is the name of the function in R, right? And typically it doesn't work really well when you name your variable same as what other things in R are named by default. So average is going to be mean, okay? Mean of account data, $, column accounts. Okay, so right here, oh, it didn't show me that, right? So I'm gonna show the average. Boom. All right, and here it is. So my average is, and that is X bar, right? This is not a population mean. This is sample average. So I have 400 accounts out of God knows how many accounts, right? And that specific sample gives me $179.99. So let me call it $178, right? So therefore I'm going to say here my X bar sample average is $178. Okay, so well, in my problem it was stated that if the average account balance is above 170, right, that's my alternative hypothesis right here, then I installed a new information system, right? So X bar turned out to be 178, done deal, right? It's more than 170, so it's a green light. Well, not so quick. Could it be that the sample that I have received is a result of just random fluke? So in other words, remember what we discussed in the previous lecture. Every time when we start testing hypotheses, just like in criminal proceedings, we believe the null. Criminal court starts with the assumption that the defendant is innocent until proven guilty, right? Same thing here. My null hypothesis, right, was saying that H0, okay, was saying that the actual average is 170 or less. Okay, so, and that's what I'm believing, right? I start hypothesis testing always, for all tests. I always start the hypothesis testing by believing the null statement. And the null says that my average is no more than 170. How could that be that if my average, true average, for all accounts, for all months, is 170, right? Could it be that I picked up a sample with the 400 observations, and in this sample, the average was 178. Could that be by accident, randomly? The answer is yes, of course. It could, right? I take a different sample. That's why we discuss sampling distribution. What's a sampling distribution? It's a distribution of all possible sample averages. So if my true average account balance is 170, then the distribution is going to be centered of all possible X bars, sample averages. It's going to be centered around 170, okay? So every once in a while, I'm going to get a sample with average like this, 178, 182, 172, higher than 170, okay? In other cases, I'm going to get unlucky sample, so that the X bar is going to be 165, 150, 157. So it's going to be all over the place, right? So could it be that this 178 that I saw in that specific sample was just a random fluke, just because all counts are different, and I just picked these 400 accounts. It was such a lucky pick that the average just turned out to be 178. Yes, it could, right? Now, the question is, how likely? How likely is that to pick such an account, such a lucky account, sample, right? 400 accounts, that their average is going to be 178 or even more than that, if I still believe in null and the true average is 170, no more than 170. So in other words, I'm going to compute the p-value, right? In the previous class, we discussed that p-value, the center point of all hypothesis testing, p-value, is the probability to see what you are seeing in the sample, or even more extreme, provided that the null is true. Okay, what's more extreme? So I'm testing that I'm testing a greater than hypothesis, right? I'm looking for high average account balances, all right? And I saw 178. What's even more extreme? Even higher values than 178, right? So what I'm going to do is calculate the probability to see a sample with an X bar 178 or more. Why more? Because I'm testing the right tail for good for high values, right? Given that the null is true and the actual population mean is still 170, and that's exactly the p-value. When I told you in the previous lecture that p-value interpretation is always going to be problem specific, well, this is specific. Okay, general interpretation of the p-value is that it gives you probability to see the X bar that you're seeing, or even more extreme, if the null is true. So in my case, X bar, the p-value is going to be probability to see the X bar average sample with the sample with an average of 178 or more, if the null is true and the true average is still $170. Okay. All right. So question is, of course, how we're going to compute that. Let's see if I have that formula. Yes, I do. So we discussed in the lecture on confidence interval that each time when you pick a sample, it comes from population, and that's all you know really about the population, right? You don't know population mean mu, you don't know population standard deviation. So therefore, what are you doing really is you're calculating the X bar sample average and S sample standard deviation, which is different from the population standard deviation. Okay, and if you create ratio like this, X bar minus the true mean divided by S over square root from n, that is going to be distributed according to the T, or student distribution, with n minus 1 degrees of freedom, where n is the sample size. Okay, so this is what we're going to do. We're going to compute T statistic, so exactly that. Okay, and then we're going to find the likelihood that T is as extreme as this, or even worse, even higher than that, given that the null is true and the average balance is 170, or average T is 0, as it should be, right? All right, so let's get down to that. So we're going to compute actually, so let me outline the program from here. Okay, I'm going to calculate the p-value using T value, but that's kind of a long way. After that, I'm going to show you a much shorter way which leads to the same answer. So I'm going to show you that in two different ways. Okay, so in order to compute the T value, this one right here, I need X bar, which I already calculated, didn't I? Yes, I called it average, right? It's the mean of the sample. Mu, what we hypothesized in this formula, the true population average, according to our null, it's 170, right? Remember again, I test hypothesis by believing that the null is true. So therefore, I'm going to say mu. Let me not do that. I'm just going to use the number, because mu is also name of the parameter in the function t-test, so it can get confusing for R. So I'm not going to do that. So I need sample size n, and I need S, the sample standard deviation. So let me go ahead and calculate that stuff. Okay, so here I'm gonna erase that. Okay, so S, sample standard deviation. Remember from a few lectures ago, SD, standard deviation of accounts data, $, counts. Okay, I run that, and we did that several times. How do I find out the sample size? I mean, I know it's 400, but here's how I can do it programmatically. I can say n row, number of rows, in the dataset account data. I run this line as well. Okay, so now I'm ready to compute. Let me go ahead and actually put a comment. Compute T value. And oh god, what did I do? Okay. Compute T value. Alright, so I'm gonna say T underscore value is it's the result of this messy formula, right? So I have to take x bar minus the mean mu. I hypothesized it to be 170 divided by s over square root of m. Okay, cool. So here I'm going to say x bar is just average. Should have called it x bar, right? Let me go ahead and do that. X bar, just to be consistent with formula. I'm gonna rerun this line. So now I have variable x bar. You can see it right here in the environment, right? 177.99. Okay, so t-value is simply x bar minus mean 170, according to what I assumed in the null hypothesis, divided by big fat brackets, right? Or parentheses rather. Standard deviation divided by square root from sample size, which is n. And I computed all these things. Here's my s, here's my n. All these things are there. Okay, well, see, everything seems to be in order. I run this line. There it is. Well, let me go ahead and see what the t-value is, right? Not that it's going to tell me much. Okay, so t-value is 2.3392. Okay, and the question is now, how far is that away from zero, right? Because when I subtracted the mean, so I assume that it's x bar is distributed around mu, the true population mean. So when I subtracted x bar minus mu, I effectively drove the difference to 0. So, and that's what the average for the t, right? T is centered around 0. Okay, and I got the value of t 2. Where is that? Yeah, right there at the bottom, 2.392, right? So since I'm testing the right tail, since my alternative is greater than, then I'm looking for the values of t as extreme as 2.3392 or even more. So I'm looking in the right tail of the distribution, right? Because my alternative is greater than, and that would give me the p-value. Likelihood to see that t-value or even bigger, provided that the null is true. And null is true again essentially means that x minus mu, x bar minus mu 170 is centered around 0. Okay. All right. Anyhow, calculate p-value. Let me put underscore p value. Okay, so p-value, p underscore value is the probability in the right, in this case, right tail of the t-distribution, correct? Why right tail again? Because I'm testing mu, alternative hypothesis, mu greater than 170. Greater than means it's the right tail of the distribution, okay? So, how do we calculate the probabilities for the t-distribution? Well, p for t, right? pt. P norm was probability for normal distribution, pt is the probability for the t-distribution, okay? And we have to provide 3 different things for the p-value, right? For this function, I mean. Okay, so it's a t-value, first of all, right? T-value, which I just calculated here, a couple of lines above, right? Next one should be degrees of freedom, df. And as I start typing, it says, yep, I know that there is such thing, df. If you remember, how do we calculate degrees of freedom? It's sample size minus 1. So therefore, it's n minus 1. I'm not using sample size here. I mean, I can, right? 400 minus 1, 399. But I already programmatically, through the line of code, recorded the number of lines in my sample size into the variable called n. So that's what I'm using. And I'm looking in the right tail of the t-distribution. How do I say that to the function pt? Well, I'm going to say lower tail is false, right? Because lower tail means left, really. And I'm looking in the right tail. Okay, so then p-value. I found the p-value, and now let's see what it is. P underscore value. Kaboom. Here's my p-value, 0.009965. Okay? So that essentially is intermediate result for me, right? So I found out that the probability, so let me go back to my slides, right? Yeah, right here, okay? Here's what I computed, graphical interpretation, okay? I just found out that p-value is 0.0099, okay? So, in the previous lecture again, I told you that the interpretation of the p-value is always, it's the probability to see the sample as extreme as what you are seeing or even more extreme, provided that the null is true. So, specific to this problem, probability to see sample as extreme as 177.99, let's call it 178, or more. Why more? Because that's what my alternative says. Greater than, right tail. The likelihood to see the sample of average 178 or more, given that the null is true and the actual population average, true population average account balance is 170, the likelihood of this is 0.009. 0099. Okay? That's the plain English interpretation of p-value. Probability to see a sample with an average of 178 or more, given that the true average for the all accounts is 170, likelihood of that happening is about 1%, right? 0.0099, which is roughly 0.001. Okay, so null can still be true, right? And this could be just a lucky sample, right? 400 accounts give me 178, but the likelihood to see something like that, or even higher balance, average balance on the account, is only 1%. Okay, that's basically the meaning of what I've just calculated. Okay, and after that, what am I supposed to do? Well, again, if the probability is high, right? Remember we discussed a couple of, well, in the last lecture actually, right? If the probability to see that in a sample, 178 or more, is big, that means that my sample is not inconsistent with the 170 average. Okay, so therefore every once in a while I'm going to get sample like that, and there is nothing miraculous about that. But so therefore I'm going to stick with null hypothesis. I'm going to say, yeah, if null is true, sometimes I'm going to see the sample like that. Not unusual. So null still stays. I don't have any grounds or evidence to reject the null. But if the probability is small, then I'm going to say, well, two different alternatives. Alternative number one, what I just saw is a very rare sample. And indeed it's rare, right? Things like that I'm going to see only in 1% of the cases, right? If the null is true. So this is a rare event, almost a miracle. Or another alternative, I'm going to say there are no miracles, and null is just simply not true. That means that I have to move this average closer to 177, then this becomes believable. Okay? And therefore I reject the null, so I claim that I have enough evidence in my sample to support the alternative, reject the null, and support the alternative. Right? And all of that is based on, is that a high p-value or is it a low p-value? Well, in the previous lecture we discussed low compared to what, or high compared to what? What's the judgment point, right? It's 1% p-value. Is that high? Is it low? I don't know. So what does our problem say? Our problem doesn't say anything, right? No, that's not the problem. Problem right here, okay? Our problem just says, is the average higher than 170 or is it not higher than 170? Okay, so, and we discussed that there are three different p-values that are being standardly utilized by statisticians, right? I can use p-value of 10%. In this case, I'm going to call it a weak test. I'm going to use p-value of 5%, and that is usual, default, standard, normal. Not standard normal, but standard or /normal. All right. Or I can use alpha, significance level of 1%. In this case, it's going to be a strong test. And by default, statisticians are using 5%. All right. So that's what I'm going to do. A couple of slides later, that's exactly what I'm doing. So I'm comparing p-value with my significance level, 5%. And what do I find? P-value is small compared to my chosen significance level alpha. So therefore, probability to see a sample like that with an average of 178 or higher is actually small if I still believe in the null hypothesis. It's not very likely to see a sample like that. So what do? I reject the null, right? Again, the rule of thumb, which applies always in all hypothesis testings. If the p-value is small compared to significance level alpha, I reject the null in favor of alternative. If p-value is higher than alpha, I fail to reject the null in favor of alternative. That's how we conclude the test. In my case, p-value is smaller than alpha, so I reject the null in favor of alternative. And what do I see? So I reject this statement in favor of alternative. And now I state that I do have this sample does supply me with sufficient evidence to state that the true average account balance is higher than $170. So therefore, based on this test, I'm going to proceed and probably install the new accounting information systems. Okay, so that's the conclusion of my test. I reject the null in favor of alternative because p-value is small compared to alpha. Right? So this is a long way how we can do this this test, and I promised you that I'm going to show you the short test. And short test is done by using the function t.test. Okay, so here's how the function t.test works. Okay, so t.test, let me tell you right off the bat that t.test will give me the same answer. All right, the p-value, that's the final thing that I want out of any hypothesis test. So I guess I'm going to put a comment here and say alternative shorter way to test hypothesis. Okay, so I'm going to use the function t.test. T.test. All right. And the function takes a few parameters, as you probably have guessed by now. Parameter number 1 would be what is the data set that we're trying to test. My data set is called accounts data, and the column that I'm testing specifically accounts. Okay. Next one is what is my hypothesized mean. In other words, what do I write in my null and alternative hypothesis as a number? So population mean mu is 170. That's what we were testing, right? And also, remember we discussed that in the previous lecture, the alternative can take 3 different forms, right? It can be not equal. In this case, I have to use 2 dot sided, right, as the next parameter. So parameter is called alternative. Okay, equals, quote unquote. Okay, so here my options are 2 dot sided if my alternative is not equal. So null is equal, alternative is not equal, or it's less. So mu less than certain number, right? Or greater than a certain number. So in my case, let's see, what was my alternative here? My alternative was that the average account balance is greater than $170, right? Okay, excellent. So and that's exactly what I have to put, right? So according to my hypothesis, what I'm testing is that the true population mean is 170 and alternative is greater. Okay. All right. So I'm going to run this test, and that's what it gives me. So a bunch of different numbers, right? So first of all, it gives me the t-value that it computed, right? Didn't we compute the same thing? Yeah, we did, right? Earlier. So here's the t-value that we calculated. Here's the t-value that the t-test function calculated. Oh, looks pretty close, right? Not exactly. So mine was more detailed, right? 2.339287. They rounded to 93. Degrees of freedom is 399. Not a big surprise. We knew that. 400 minus 1. And the p-value right here, 0.009907. Mine was right here, the p-value 0.0099065. So again, this is rounded, right? So this is a different, much shorter way, right? So you can do hypothesis testing like this. and arrive to the p-value, or you can just simply run one line and get pretty much the same result, right? So I wanted to show you both ways. Just make sure that we're on the same page, and you know the internal workings of the test. Okay, cool. All right, so now let's go ahead and discuss something else. Now that we know how to test the hypothesis, let's discuss normality testing. Okay, so we did that. We concluded the test. Yeah, testing for normality. Okay, so remember how we started looking at this problem? We started by saying, hey, we need to take a look at the histogram, right? Because if histogram is not looking normal, that means that it's not going to end well. The results are not going to be very useful, right? So therefore, normality, the sample should be normally distributed, bell-shaped distribution, was one of our requirements. Okay, that's great. But there is another way to test normality, and it's a little bit more rigorous than just looking at the histogram, right? This is something that's called Shapiro-Wilk test for normality. And again, just like in any other case, it has two different hypotheses. There is a null and there is an alternative. The only difference is that null looks a little bit different from mu equals to something versus mu not equal to something else, right? So our null hypothesis is going to be that the data in my sample are distributed normally, statistically normally. So I'm not going to go into the details what exactly this test does, but it looks, it basically calculates the average of the population, standard deviation, and you remember the rule, right? We discussed it several lectures ago, that if you go from the mean, if the data is truly normal, if you go from the mean plus or minus 1 sigma, you will get 68% of everything, right? If you go plus or minus 2 sigma, you'll get 95%. Plus or minus 3, you'll get 99%. That's what basically makes up the normal shape. That's what Shapiro-Wilk essentially does. Okay, so it's kind of brief synopsis. All right. Anyhow, so and let's agree from now on that every time when we run the Shapiro-Wilk test, first of all, we're going to get a p-value, right? That's how every single hypothesis test is performed. Run the test, the output, the result of the test is actually the p-value. And then we compare p-value against alpha. If p-value is less than alpha, we reject the null. If it's greater than alpha, we fail to reject the null. That's basically how we conclude the test, right? But we have to pick the level of alpha. So let's make this pact from now on, that each time when we test numerical data for normality, we're going to use standard value of the significance level, which is 5%. For other tests, not for the normality test, but for something else, I can specify for you, like, do this test at 1% significance or at 10% significance, okay? But let's do the normality test always at 5% significance level, okay? And this test is really simple. So let me show you really quickly. So in order for me to see if Shapiro-Wilk test tells me if the population is not normal or not, let me illustrate that, okay? Shapiro-Wilk test for normality, okay? So here's what I'm doing. Remember how we did the t-test? We said t.test. Shapiro-Wilk, pretty much the same thing, right? I'm gonna say Shapiro, and there is such thing, built inside the R. Instead of t-test, it says Shapiro.test. Okay, and all I have to do really is to send the argument as an argument to this test, as a parameter to this function Shapiro.test. I'm gonna send the variable that I'm trying to test. So in other words, a bunch of numbers, right? A bunch of numerical data points, and that is called, how did I call it? Accounts data, the $sign accounts, right? So take 400 numbers and test if they are normally distributed or not. I run this line, So it's very simple, right? You just call Shapiro test, tell it what exactly do you need to test, and then it spits out the results for you. So here is the result. And again, the most important outcome from this test is what? A p-value. Right here is my p-value. Okay. So what do we see, ladies and gentlemen? So we see that, let me type it right here. Okay. So my null that I was testing was what? Data are normal. And the alternative that I was testing is H1, data are not normal. Okay, not normally distributed. So here's how I conclude the test. P-value is what? I got 0.1711. Okay, and what do I compare it against? We discussed that just 2 minutes ago. I compare the p-value against alpha, and for normality test I will always use standard alpha, right? 0.05. Well, it's clear that my p-value is higher than 0.05. My p-value is 17%, and the significance level is only 5%, right? So what happens when my p-value is higher than alpha? I fail to reject the null hypothesis. So null stays. So what does it tell me? That the data, this distribution right here, the shape is looking very much like normal distribution. So now not only visually I see that the shape is kind of normal, but I have now my confirmation numerically. Okay, so the data are normally distributed. Again, very important thing that we're going to actually use more and more as we go through this semester, because later we're going to get into the testing for two different populations, many different populations. So each time when we run that type of test, we have to make sure that the samples are normally distributed. Okay, but in other tests, when samples fail, so question is, okay, what if it says data are not normal? So what if my p-value, for example, right here would be 0.017, and it's less than 0.05, and data are not normal? Then what? Well, that means that I cannot use t-test, I cannot construct confidence interval, I have to use something else. And that something else we're going to call non-parametric tests, but that we're going to discuss at the end of the semester. Okay? So each time when we have a problem going on, we're going to basically, with numerical data, right? Another important, I guess, consideration. All of these things, normality, histogram, etc., they apply only to the data which are actually numbers. So if you have categorical data such as customer ratings or something like that, there is no mean, there is no variance, there is no normality. None of that exists. Okay, so everything that we discussed so far applies only to the numerical data sets. Okay? Alright, so we have some time left in this lecture, so let's go ahead and do another example. So this one right here. Okay? Revenue management. Many ski resorts, ski centers, base their projections of revenue and profits on the assumption that the average ski enthusiast go into the mountains to ski, stay at the resort, spend big bucks for 5.5 days on average per year. Okay, it doesn't have to be integer number because we're talking about average among many people, right? It doesn't have to be precise integer. All right, so that's basically their assumption. To investigate if this is actually true or not, they take sample of 100 people who like to go to the mountains and ski, and they ask every one of them, how many days did you stay in the ski resorts last year? So can we use alpha? This is alpha, right? Significance level of 1%, if their assumption is wrong or not. So note that here I'm not asking, this problem is not asking us like, is the average higher than 5.5 or is it lower than 5.5? It just says, can we infer that this is wrong? What is wrong? That the average is equal to 5.5. So that means that what we're trying to say is wrong means it's just not 5.5, right? It can be higher than that number or lower than that number. So therefore, ladies and gentlemen, here is how the hypothesis is being formulated for that specific problem, right? So our challenging assumption, alternative hypothesis, says that the average number of days that the skiing enthusiasts stay in the ski resorts is not 5.5. It's different. How different? Is it higher than that, lower than that? Just different. Okay, can be higher, can be lower. Both possibilities are included. Okay, and my null hypothesis is, if you remember, we discussed that, right? Status quo. In other words, what makes them, the problem to feel okay and comfortable? That's what makes them feel okay, right? If that is true, and on average 5.5 days per year, the ski enthusiasts spend in a mountain, that is just the right spot on the money. Okay, so this is our null hypothesis, and alternative is not equal, right? So two things, of course, right? Thing number one, before we start doing anything, we have to make sure that the normality is satisfied, right? And this time around, we're going to do both tests, right? So I'm going to start a new problem here. So I'm going to include a bunch of pound signs. Oops. Okay. So ski resorts, right? Ski resorts. All right. Okay. So number one, of course. How did I call the variable, the data frame? Skiing data. Okay, cool. Skiing. I just want to be consistent with what I have put in the slides, right? Skiing data is read file, read CSV from the file c data skiing.csv, I believe is the name of my file. Yes, it is. So let's take a look at the structure. Again, this is not a required step, but I like to do it anyway, just cause. Okay, just because I can, right? Skiing data. It has 100 observations, just like advertised. One variable, one column. It's called number of days in the mountains, ski days. Okay, very cool. So this time around, actually, I'm not going to go through both steps. All right, I'm not going to calculate the t statistics. First of all, x bar. Well, actually, let's calculate x bar, but nothing beyond that. Okay, so average, right? Well, x bar. By now, you probably know that x bar means sample average, right? So I'm going to calculate the mean for my data. That would be skiing data and column ski days. Okay, them. And now I have to show x bar, and x bar right here 513. Alright, so that may or may not be a problem, right? So let me kind of be more specific. Let me explain in more details. What do I mean by that? If you remember from the slide, the assumption that they make to project their revenues is that on average people go 5.5 days per year into the mountains and ski, right? I took a sample of 100 observations, and it turned out that in my sample of 100 people, the average was 5.13. So it looks like we're falling short, right? And it could be an indication that our assumptions are overly optimistic, right? We believe that they spend 5.5 days, but in actuality it's 5.13. Shorter average stay means shorter revenues, right? They spend less money sitting in the bars and restaurants or going through the gift shops and stuff like that. Okay, so one possibility is that I'm too optimistic, right? And my actual average is not 5.5, likely it's lower. Or alternatively, I can say, well, if what's the difference between 5.13 and 5.5? 0.37 doesn't seem like all that much, right? So could it be that the difference between 5.5 and 5.13 is just simply because it was a random sample? I got 100 numbers and it just happened to have the average on the low side, while in actuality it's not that different. I mean, if the true average is 5.5, every once in a while you get sample like that. It's not unusual. That might be, right? How do I judge? Again, I compute the p-value or the probability to see what I'm seeing in the sample, or even more extreme, right? And that is called p-value. If p-value turns out to be small, then I'm in trouble, right? I'm going to reject the null hypothesis in favor of alternative. But if p-value is large, then I'm going to say, yeah, no problem. Sample like that comes up every once in a while. It's pretty consistent with my null hypothesis, 5.5 on average. So no reason to worry. Okay, so how do I compute the p-value? Again, I told you that I'm not going. Oh, whoa, hold on there, right? What we didn't check is normality, right? Important step. I'm ready to jump right into the battle, but we didn't check normality. So check normality, because if normality doesn't check out, then all of that is pretty much moot point, right? So first of all, let's do it visually, just because we are used to that, right? So histogram, HIST, for the data, skiing data, and column ski days. All right. So here's my histogram. Wow, it looks so beautiful, almost perfectly symmetric. So I'd say it's normal, even without running the Shapiro test, but just to be strict about that, so let's go ahead and run Shapiro-Wilk test, right? And I'm testing again the same exact thing, skiing data, column, ski days inside of that. So I'm gonna run that a test, and there it is, okay? So it tells me that my p-value, so let me go ahead and do it right here, okay? So p-value for Shapiro-Wilk test is point 0.069, right? And it is, from what I can see, higher than 5%, which we decided to use as a standard for test for normality, right? So my p-value is higher than alpha. What do I do? Again, this is what I'm testing, right? I wrote that down in the previous problem. Now, data are normal. Alternative data are not normal. My p-value is higher than alpha. If p-value is large compared to alpha, I keep the null hypothesis. Or rather, better to say, I fail to reject that in favor of alternative. Well, it's the same thing as keeping the null, right? So therefore, the sample does not provide me evidence that the data are not normal. They're still statistically normal. So thank God I can proceed, right? So now let's go ahead and run the t-test, right? So I'm not going to compute all these x bar minus mean divided by s over the square root of n, and then use the pt function to find the p-value, right? So I'm just going to go straight for t-test. Okay, so how do we do the t-test? Well, we have to first of all supply the set of data that we're testing. So it's skiing data, $ skiing days. All right. Next one is what is the mean in our hypothesis? Mu, population mean. We hypothesized that on average people spend 5.5 days in the mountains, right? That's what I have in my hypothesis. All right. Next one is form of alternative, right? Alternative can be either greater than or less than or two-sided. So in my case, let's see, where is my, here, right? It's two-sided, right? I'm not testing any specific tail of the distribution, right tail or left tail, because my alternative simply says not equal. Not equal can go both ways. Not equal on the high side, higher than 5.5, or not equal on the low side, lower than 5.5, right? It's only when it's greater than or less than, that's when I use the less or greater. So this one is, I have to say alternative is quote unquote 2 dot sided, okay? And you have to write it specifically exactly like that, right? So I can show you. So here, when I run this line, it works, right? So here's the result of my test. But if I say 2 sided with a space or 2 sided with a dash, it's not gonna work, okay? So it has to be exact, precise. 2 dot sided. Bam. All right. So again, the most important outcome is of course my p-value right here, right? P-value is 2.2 e minus 16. Is that right? Yeah, looks like it's right. Okay, so 2.2 e minus 16. Okay, so what do I do with that? Because for some reason I thought that it's a little different. Hold on. That's my normality test. Oh, yeah, before that I had a different result. That's strange. Let's see. 3 days. Oh, I see. That's the reason. Okay. So I made a boo-boo. So sometimes MMU. I'm actually surprised that it did run when I made the boo-boo right here. So you have to be precise. I misspelled mu. I spelled it MMU, and it gave me a different result. Okay, so now I have everything named correctly, and here's my p-value, 0.06367. All right. So now let's go ahead and conclude the test, right? There is not much left actually. So we have to compare that p-value against the significance level. What's the significance level that we were trying to use in this problem? So let's see. Right here, can we infer at 1% significance level? All right. So what do we see? P-value is 0.06, and it's clearly greater than 0.01, which is 1%, right? So p-value is high compared to alpha. What do I do when p-value is high compared to alpha? I fail to reject the null hypothesis. In other words, the average that I was seeing, what was that? The average 5.13 days is not that different from the hypothesized average 5.5, given that my number of days that people spend at the mountains has some distribution width. So in other words, every once in a while you collect 100 people, ask them how many days they spent last year in the mountains. They give you a bunch of numbers, you calculate the average, you will calculate 5.13, and that's not that unusual, okay, even though the true average was 5.5, right? So this value that I'm seeing is not very inconsistent with 5.5, right? It's still believable, because that kind of sample we're going to see in about 6.3% of cases, right? Sample that extreme or even more extreme than that, okay? And that's not a small probability, because my measure of small that I selected, significance level, is only 1%, 0.01. So therefore, my null stays, and I still keep believing that the average is 5.5. Or I should better say, the sample does not provide me enough evidence to conclude that the average is not 5.5, right? Even though it seemed to be on the low side, but it's still fairly consistent with 5.5, because that happens every once in a while, right? So that's almost everything that I wanted to tell you in this lecture. There is only one more thing, okay? The interpretation. Remember how we did graphical interpretation for the previous problem when we tested the right tail of the distribution? Let me show you what the p-value is in this case, right? So here's what we looked at. We believe the null is true, and if null is true, then the average is 5.5, right? So that's our initial assumption, that on average people that go to mountains spend 5.5 days. So we believe null, and therefore that's how all possible sample averages are distributed, with the same mean, right? Because when we discussed sampling distribution, we saw that sampling distribution has the same average as the population distribution. In this case, it's 5.5, right? So the sample that we saw is 513, right? It was on the low end, and that kind of made us doubtful, right? We're like, okay, it may be not 5.5, we may be too optimistic about that, okay? But if the null is true, this 5.13 could have been on the other side just as well, right? Because of the symmetry, same probability, okay? So in this case, the probability to see what you're seeing, or even more extreme, actually is split evenly between the two tails, okay? How large is the distance between 5.13 to 5.5? Well, I believe it's 0.37, right? That's how much difference between 5.5 minus 5.13, 0.37. So if I take the 5.5 and add the same distance, 0.37, I'm going to get 5.87, right? So this sample with an average 5.13 could have been on the other side of the 5.5, hypothesized mean. Okay, so in this case, p-value is probability to see something like that, or even more extreme. But curiously enough, more extreme means it's either numbers which are below 5.13, the averages, sample averages, which are below 5.13, or above 5.87. That's what we mean by more extreme. Because again, by randomness, my sample, if the null is true, my sample could have been on the other end with just the same probability. Okay? So when we're testing hypotheses equal versus not equal, then my p-value is sum of the areas in both tails. So if I take tail in the left, below 5.13 in that case, or above 5.87, sum of these two tails will give me that p-value, 0.06367. So when I'm testing alternative hypothesis mu greater than a number, just like what we did in the previous problem about accounts, right? I'm looking in the right tail. So this would be the only area that defines my p-value. If I'm testing alternative less than a number, then all of my p-value is the area in the left tail, and that's it, nothing else. But when I'm testing equal versus not equal hypothesis, then I have to add together right tail and the left tail of the distribution, and the sum of the two will give me the p-value. So I just wanted to point out that fact. Okay, that's the difference between two-sided test versus greater or less test versus one-sided test. In one-sided test, your p-value comes from one tail of the distribution. In the two-sided test, it comes from both right tail and left tail combined. Okay, so this is it for this lecture. It went a bit over what we typically have planned, but in the next lecture we're going to actually take a look at yet another example when we're testing the population mean, and also another one where we are discussing population proportions.